Question 21. A glass rod is charged when rubbed with silk cloth because. Now, the glass rod has free electrons which are less tightly bound. So, when it is rubbed on the silk cloth, it transfers these electrons to the silk and then it ends up with a net positive charge. So, that means that our answer is A. It transfers negative charge. Question 22 says addition of trivalent impurity to a semiconductor. Now, we know that a semiconductor is a material that, you know, is neither an insulator, neither a good insulator or good a good conductor. For example, silicon, and impurities are usually added to semiconductors in a process known as doping, to try and make them good conductors, you know. And one of such is this trivalent impurity. What does the word trivalent mean? It means that this valency of this particle that has been added is 3, right? Now, what you need to know is that let's take silicon, for example. Now, silicon's valency is 4, right? Meaning that it requires 4 electrons to make it a complete shell. But this trivalent impurity that is being added only has 3 valence electrons, right? Meaning that when it shares its electrons with silicon, for example, only 3 of the 4 electrons that silicon has, will be able to participate in the sharing of electrons between this impurity and silicon, which is a semiconductor in this case. So when it does that, the 4th valence electrons of silicon will be left, alone, thus creating something called a hole. So the answer to this question is A. It increases the number of holes. Question 23. A charge of magnitude 1.6 times 10 raised to power minus 19 coulombs is placed in a uniform electric field of intensity 1200 volts per meter. It says we should calculate its acceleration if the mass of the charge is 9.1 times 10 raised to power minus 31 kilogram. So like we've always done, we first write out our parameters. We're given the charge to be this, we have our electric field intensity to be this, and we're given the mass to be this. So we know that the electric field intensity is or can be gotten by the force divided by the charge. Now, if we make force the subject of the formula, then that means that force is electric field intensity times charge. And so, but remember that force is also mass times acceleration. So that means that we can equate these two together because they are both formulas for force. So that means that E, the electric field intensity multiplied by the charge, is equal to the mass of the particle multiplied by the acceleration of the particle, which is actually what we are looking for. So the acceleration now being made the subject of the formula now becomes EQ all over m. So we substitute each of these values into their respective places. And when you do the solving, you are going to end up with 2.11 times 10 raised to the power 14 meter per second squared, which is our acceleration. And that is option B. Question 24 says, the defect of the eye lens which occurs when the ciliary muscles are weak is called. And the first option here is long-sightedness, which is also known as hypermetropia, right? And the second option is short-sightedness, which is also known as myopia. Now, these two eye defects are caused by problems with the lens and the cornea, right? So they have nothing to do with the ciliary muscles being weak. So those two options are removed. Now, and this, for example, long-sightedness occurs when you are able to see things that are far away, but you have difficulty seeing things that are close. Short-sightedness is the opposite. You can see things that are close easily, but are unable to see things that are far away. Now, astigmatism occurs when the cornea or lens has mismatched curves. Astigmatism happens with age when old people generally, is more prevalent with old people. Their sight becomes blurry and they can't identify things again. but that has to do with the cornea and their lens having mismatched curves. But then the answer to this question is presbyopia, which is when the eyes are unable to adjust the lens, and that is because the ciliary muscles in this case are weak. So our answer is C, presbyopia. Question 25. A light of 6.22 electron volts is incident on a cadmium surface. If a stopping voltage of 2.1 electron volts is required to reduce the photocurrent to zero, calculate the work function of the cadmium in electron volts. Now we're given the photon energy. Photon energy simply refers to the light that was incident on the surface. So we're given our representative is E was given as 6.22 electron volts. Now the question also made mention of a stopping voltage, also known as a stopping potential of 2.1 electron volts, 2.15 electron volts, and it is required to, or this voltage is required to reduce the current to zero, and we're asked to find the work function. Now, Einstein has the photoelectric equation, which is denoted by the stopping voltage EVS is equals to the photon energy subtracted, or which subtracts the work function. And so we make the work function which we are looking for the summation of the formula, and so we bring this the other way and we substitute these values here, and that simply gives us our answer to be 4.07 electron volts, which is answer A, option A. Question 26. The fundamental frequency of an open organ pipe is the same as that of the second overtone of a closed organ pipe of length 0.2 meters. We're asked to find the length of the open organ pipe. Now we know that the second overtone is the third harmonic, right? So this is our closed pipe, and we can see here that it is the second overtone, right? Or a closed pipe representing the second overtone, and we're given the length of this pipe to be 0.2 meters. And we know that for the second overtone or third harmonic, the formula for length is 5/4 of the wavelength, because there are 5/4 wavelengths here when you calculate it, from this diagram. And so we're given the length to be 0.2, we put it into this formula, and that becomes 5/4 of the wavelength. We multiply and make the wavelength subject to the formula, and that gives us the wavelength to be 0.16. But remember that the question asks us for the length of the open organ pipe. So now this is our open organ pipe, the fundamental open organ pipe, right? And we know that for the fundamental, we're given the fundamental frequency, or we're told the fundamental frequency, and that means that we're also looking for the fundamental length. That's why we're representing it with L subscript naught, right? And the formula for that is simply half of the wavelength. So we've already gotten the wavelength from it. The wavelengths for these two are the same, because the question already told us that the fundamental frequency of this is the same as the third harmonic of this. So that means we can take both wavelengths to be the same. So that becomes 0.16 all over 2, and our answer is 0.08 meters, which is option D. Now question 27 says, what is the maximum possible wavelength in an open organ pipe of length ACM, right? One thing I need you to know is that the maximum possible wavelength will correspond to the minimum possible frequency, right? And the minimum possible frequency for a pipe system is the fundamental frequency. So for this open organ pipe, we know that we're given the length to be ACM, and we know that for the fundamental frequency of an open organ pipe, the length is denoted by half of the wavelength. So that means that the wavelength will simply be twice the length, which in this case is A, and so our wavelength is 2A, which is option B, 2ACM. Question 28. Mercury is used as a thermometric substance because, and we're given three options here. We're told its specific heat is low, it does not wet glass, and it is opaque. And mercury actually fulfills all these conditions. It actually has a low specific heat, meaning that the temperature can be increased quickly. So that means that it can easily show the temperature. It can easily show the temperature. People ask, okay, why is water generally not used as a thermometric substance? It has a higher specific heat than mercury, meaning that it is going to take longer for the temperature rise or the temperature change to be obvious. So the specific heat of mercury is low. Another reason why water is not used is that it wets glass. You see, and when it wears glass, it makes it difficult to be able to know where the actual reading is. So mercury is also used because it does not wear glass. And then finally, it is opaque, right? It's an opaque substance, meaning that you cannot mistake it for the for the for the transparent thermometer, right? So that means that in this case, our option is D, which is all options. Question 29. The magnetic field inside a solenoid is it's uniform. The magnetic field inside the solenoid is uniform. Question 30. A gun with a muzzle velocity of 500 meters per second shoots a bullet at a bird 50 meters away. Now, to hit the target, the question asks the gun should be aimed from what direction, and we're given all these options, and we're given the acceleration due to be gravity to be 10 meters per second squared. Now, this is a quick diagram just illustrating the the parameters we're given. Now, it tells us that the muzzle velocity is 500 meters per second, as we can see here. It also tells us that it is shooting the bird from 50 meters away. The horizontal distance is 50 meters away. And then it's asking us for this vertical distance, which is denoted by h here. So now we know that one of the equations of motions is this, right? Where s is displacement and it is equal to the initial velocity multiplied by time plus half of acceleration due to gravity multiplied by time squared. Now we're going to be dealing with the horizontal components because we know that when it comes to projectiles, we have both the horizontal components and the vertical components. So, and they normally denote the horizontal components with a subscript of x because this is the x-axis, and the vertical component with a subscript of y, as will be later seen. So that means that in this case, our distance or our displacement is going to be s subscript x, and our acceleration due to gravity. Now we know that acceleration due to gravity is a vertical occurrence. It doesn't happen horizontally. It only affects things that are in a vertical form of motion. So in this case, our g, which is gx, will be 0. There's no acceleration due to gravity that is acting in the horizontal direction. So we're now so this equation will now look like this, right? Because we've taken all the horizontal, we've labeled them all the horizontal ways. And we already said here that gx is 0. So that means this goes away and our equation is now simplified to this. My equation is now simplified to this, right? So now we make the time the subject of the formula, and we already have the horizontal distance, which we are given as 50. We have the horizontal velocity and the initial velocity, which we were told is 500 meters per second. So when we divide this, we get our time to be 0.1 second. Remember that we're looking for h, so this is just for the horizontal components. Now we'll go to the vertical components. Now for the vertical component, like I mentioned earlier, the displacement is basically the height, the vertical height. Our g is gy, and now we know that acceleration due to gravity works in the vertical form of motion, and we're given to be 10 meters per second squared. So we illustrate that here. And so we rewrite this formula in the vertical way. So our s, which is this s now becomes h here. The u becomes u subscript y because we are dealing with vertical component, and every other thing takes its vertical form, right? Now we know that the distance we're given was the horizontal distance, so that means that our vertical distance will be 0. So this becomes 0, and so our formula is once again simplified to just this, right? So we substitute the value, so this becomes half times 10 times 0.1 squared, and so when you multiply all this, you get your answer to be 0.05 meters, but the options were in centimeters, so this becomes 5 centimeters, which is option A, 5 centimeters high above the bed.